In Gen Chem, you will have talked about acid-base reactions in the context mostly of strong acids and strong bases. And these would react to form a salt plus water. So if you remember, you'll take the anion of the acid plus the cation of the base. Those will make your salt, your neutral salt, and H and OH make H2O. In organic, however, we do this a little bit differently. And I'd like to refresh your memory on a definition of acids and bases, specifically the Bronsted-Lowry definition of acids and bases, where Bronsted-Lowry acids are proton donors and Bronsted-Lowry bases are proton acceptors. It's found right here. We're going to be talking today, the first time, likely in the organic videos, about reaction mechanisms. And reaction mechanisms they govern chemistry as a whole. But in organic, we use them a lot. So, drawing a reaction mechanism is a really important skill in organic chemistry. We're showing the movement of electrons, which gives rise to the products of our reaction, and we use what we call curved arrows to do this. Okay? So you will show a curved arrow, shows that electrons are moving. This will give rise to chemical changes. So in the first mechanism you draw, it's going to be a really, really generic example of a typical base plus, monoprotic, unknown weak acid. In Gen Chem, you'll have called them HA, so I've called them HA for you today. But the steps in the generic one-step acid-base reaction mechanism are... And basically what's going on is the lone pair, LP, of the base deprotonates the weak acid. Actually, let's take weak out there. Let's just go with deprotonates the acid, because it would work with strong acids too. Then the bond between the hydrogen or proton of the acid and the anion of the acid breaks. So, one arrow is going to make a new bond. The other arrow is going to break the previous bond. So how do we do this? So we draw a curved arrow from the lone pair of the base to the proton of the weak acid. So we just take it, we draw, making a new bond from that lone pair with the hydrogen. Then we need to show this bond, hydrogen with the anion of the acid, breaking. So those electrons will come off. And I actually want to do all my arrows in red. So our products, in terms of organics and organic acid-base reactions, is you're going to have your base with another hydrogen I'll draw that lone pair in another spot. It looks a little weird. Plus the anion of that acid. So we pop that bond off. 2 electrons go onto that negative species, which makes it negative, actually. So 2 electrons, go onto the rest of the R group of that acid, makes it an anion. Now we're good. So, if you don't have any of that, go ahead and draw that in. And we're going to move on to an actual reaction and mechanism. So how I'm going to do mechanisms and reactions in my personal videos is we're always going to write the overall reaction first, then we will draw through the mechanism. So, we've talked a lot of times, interestingly enough, that water can be an acid or a base, and this is dependent on what it's present with. In this case, it's acting as a base since we have an acidic proton right here. So this substance is our acid. This substance is our base. Whoops. And what we're going to do is we're going to try and draw the products like what we have here. So our base with an extra hydrogen and the negative R group of the acid over here. So we're going to learn how to draw products. So this is our base. This is our acid. So remember, it's going to be base with another hydrogen plus the negative R group of the acid. So now we can draw that. So we're going to draw our water. Sorry, we'll leave that on the screen here. One lone pair is left over. We have that extra H on there. Positive charge on that oxygen. Plus, and now you get to practice your drawing, which is always great. So we're going to put this O here. So it had two lone pairs on it before. Now it has that extra lone pair and a negative charge. So now we're going to draw through the mechanism of how this happens. So if you're predicting the products, right, this is our base. So this is its conjugate acid. This is our acid. So this is our conjugate base. Okay, notice that these reactions are in equilibrium because then, right, so if this is our base and this is our acid, we could form a bond, take a proton off, and we could go back to here. So let's draw in the reaction mechanism, and I'll leave that on the screen for you. So remember, step one is we're going to draw a curved arrow from the lone pair on the base to the acidic proton of the acid. So I'm going to draw a curved arrow from here to here. Actually, make it a little nicer. There it is. And then, since we formed a bond to hydrogen, we need to break this bond right here. So we'll break this bond. Remember, it's from the center of the bond to the atom that still remains on the species, right? To that end of that R group. So now we can draw products, right? So we're going to draw our base with an extra proton. One lone pair is left, positive charge. And we drew these before, so I'm just throwing these down really quickly, and take your time drawing it if you want. So that is how we would draw through the mechanism for an acid-base reaction. The last thing I'd like to talk about in this particular video is predicting which reaction is favored in equilibrium. Okay, so whether the forward reaction is favored or the reverse reaction is favored is actually dependent on the pKa, okay, of our reactants or our starting acid, or the pKa of our product, our conjugate acid, right? So which pKa is higher, meaning which is more stable or less reactive. So, again, you can read these bullet points right here. I like to talk through them and not really just read straight from the page to you, but that's just for your personal reference. So we're going to draw the mechanism for this reaction. We're used to doing this, so we're going to draw a curved arrow from the lone pair of our base to the proton of our acid. We're going to break that bond onto the carbon. We're going to draw and remember, you don't have to draw bonds to hydrogen in. I drew them both in so that you knew they were there, as in those are the protons that are coming off. So, our pKa is 15 here. Our pKa is 18 here. So, in this particular case, equilibrium favors the forward reaction because 18 is greater than 15. So the products are more stable than the reactants, and therefore the products are favored. So I'm glad this video stayed at a manageable length. There will be more acid-base and reaction mechanism videos to come. So I hope this helped you understand more about acid-base reactions in organic chemistry, and I hope it can be useful for you in the future. We'll see you next time.